Hi, everyone. Thank you for tuning in to today's micro lecture. We are continuing with time value of money principles, and we are going to talk about compounding a single sum with continuous compounding. So in the previous micro lecture, we talked about finding the future value of a sum when we have multiple compounding periods. And conventionally, we might have monthly compounding or quarterly compounding. But what happens when those compounding periods get smaller and smaller? The theoretical limit is that we have infinite compounding periods, and that's what continuous compounding is. So we're going to show a modified version of the formula in a few slides here, and we're going to show you how to tackle this problem when we have continuous compounding. Now let's think about the formula that we introduced when we have multiple compounding periods. We take the present value and we multiply that by compounding factor that is 1 plus r over m to the n times m power. And we show what those variables are. FV equals the future value, PV is the present value, R is the rate, the annual rate, and then M is the number of compounding periods, and N is the number of years. And this is the formula that we use when we have multiple compounding periods. We just plug in the numbers we have and we solve for the future value. So what happens when M gets larger and larger? Well, let's think about starting with daily compounding. That's going to be 365 compounding periods in a year. But what happens when we have hourly compounding? So we just multiply that, 365, 24 hours in a day, that's 8,760. What happens if we break that down by the minute? We have over 525,000. And then what happens when we break that down by the second? We have over 31 million compounding periods in the year. And we can just keep breaking that down into smaller and smaller increments. And eventually, those numbers just keep going to infinities. And that's what continuous compounding is. So let's look at the formula for continuous compounding. So as m reaches infinity, our formula becomes PV times e to the RT. Now, e is the base of the natural logarithm. I'm not going to go into the mathematical weeds on this lecture. We may upload some more advanced finance math lectures, but for now, I just want to show you guys the formula. And we look at that compounding period, we look at that compounding factor, e to the RT, when our compounding periods are infinite. E is the base of the natural logarithm. Now, we're going to see this in most scientific calculators, but it approximates 2.71828. And we can always just plug that number in manually if for some reason our calculator doesn't have it, and it gives us a decent approximate answer. And then, of course, R is the interest rate and T is the number of years. So most calculators are going to have a function that shows e to the x power. And in this case, we can take that function and just plug in whatever R and T are, the product of R and T, and we get our compounding factor. So let's run through an example real quick. We want to know what happens, the future value of $5,000 invested in an account which pays interest continuously. We're going to assume that we have 7% per year. We're going to look at that over 5 years. So here's our formula. We just plug this into any calculator. And we're going to have 5,000 times e to the 0.07 times 5. We plug that in and it's going to give us $7,095.34 rounded. So that is using continuous compounding. This is going to be the last micro lecture on the compounding of a single sum as far as the basic math that's involved. And we're going to move on in subsequent lectures to looking at the future value of an annuity, a series of equal cash flows. We're going to look at that in some of the subsequent lectures. Then we're going to move on to other time value money principles. Thanks everyone for tuning in. I hope you can like and subscribe our videos so we can continue to produce new content.